Hello, this is Mrs. Huntley. We are in Module 5. This is Lesson 2, and you should be on page 9 of your workbook. Lesson 2, the formal definition of a function, and your essential question, what is a function? Now, in class, we talked about Lesson 1. We didn't go through the entire lesson of Lesson 1, but we talked about why we use functions. We talked about how functions allow us to make a prediction. It classifies data. Maybe it might be numbers, but it might be a non-number classification, like classifying players and their heights, or gender and favorite colors, or something like that. So a function just allows us to make predictions. Sometimes it's numbers, sometimes it's not. Now, if you remember on the last module, or in the last module, module 4, we were focused on situations where they were constant. It was linear equations. And linear equations and functions are related in some ways, and you're going to see that throughout this module that we're going to be studying. So let's go ahead and work on defining a function. We're already giving you some ideas about what a function is all about, but let's talk about it a little bit more in detail. So a definition, this is going to be a two-part definition. A function is a predictive relationship. What does that mean? It's a relationship with two variables that you use to predict outcomes. So a function rule is the equation that assigns each input to exactly one output. And that phrase, each input to exactly one output, is important. That's kind of like a key here. So if you use highlighters, that's probably a part of the definition that you're going to want to highlight. So a function is a rule or an equation that assigns each input to exactly one output. And more holistically, a function is a predictive relationship between two or more things that allow you to predict outcomes. So let's take a look at the tables that are below here. And if you notice, the table on the left is the table from Lesson 1. This is the rock that's falling off the building. It's a non-linear relationship, but it is a function. The table on the right, take a look at that and see, does it meet the qualifications or the definition of what we said a function was? We said a function assigns each input to exactly one output. The inputs are your x values. So these are your inputs. And your outputs are your y values. So inputs are on the left, outputs are on the right. If we look at the table from Lesson 1, which we've already talked about and we've already said it is indeed a function, I want you to look at all the values for x. Are all the values for x unique? And what I mean by that is, are they all different? Do you see any value that's repeated in the x column, or do we have all unique numbers in our x's? That's what we're looking at first. Let's see, we have 0.5, 1, 1.52, 2.53, 3.54. Nope, they're all unique, aren't they? There's no number that's repeated. Let's look in the other table, the table on the right. Again, looking at the x values. We have 0.5, then we have 1, oh, then we have 1 again. Now, when we're talking about a function, the input, the x values, are assigned to an output, the y values. So when we look at 1, the first one, it's assigned to 4. Okay, well, that makes sense. We've seen that before. That's not a problem. But then again, we have 1 again, and it's assigned to 36. Right there, when we have two inputs that are the same, 1 and 1, and they're assigned to different outputs, we know that it is not a function. Why is it not a function? We can't use this data to make a prediction. I don't know if 1 is going to be closer to an output of 4, or if 1 is going to be closer to an output of 36. I can't predict what it's going to be based on this information. Is this wrong information? No, it's not wrong. It's just not a function. I can't make a prediction using this information. So that's why that key in the definition of assigning exactly one output is kind of important. Not kind of important, it's very important when we're talking about a function. So if the input assign more than one value, or if the same input assigns more than one output, it is not a function. So the table on the left assigns one output value, one output y, to each unique input value of x. The table on the right has several outputs y assigned to the same input of x. I said several, and I do mean several because there are a couple of different instances. If you look down here, we've got 3 that's assigned to 99 and 3 that's assigned to 196. And again, is it wrong? No, it's not wrong necessarily. Maybe we're talking about different people and they are wearing big numbers with the same number on them or something like that. I don't know what this data is actually representing, but it's not a function. This data, the table on the right, will not allow us to make any predictions with any level of accuracy that's going to help us to predict whatever it is we might be trying to predict. Okay, let's move on. So down here, we have D assigns 4 to, D assigns 16 to. This is different language. It's a different way of talking about it. So if we're talking about our function being called function D for whatever reason, this is function D. And D assigns 4, the output, to what input? That's how we talk about it. That's how that's the phrasing that we use with a function. So 4 is assigned to 0.5. That's the input that produces that output. D assigns 16 is here, to 1. You're just reading the table, and you're reading the table kind of backward. So go ahead and fill out the rest of them. You can pause the video for a moment, fill out the rest of them. 36 is assigned to, and continue on that way. Okay, so there are the answers. And again, the output is assigned to a specific input. The inputs should all be different. If we had another instance where there was another 1, if we were representing this function and we had another 1, the output would have to be the same in order for it to be a function. So again, if I had another number 1 down here, my output would again have to be 16 in order for it to truly be a function. So where have we maybe seen this before? We've been talking about inputs and outputs. Who remembers back to elementary school when you might have had an input-output machine? I can remember that. Back in the olden days, I had an input-output machine, and it might have looked something like this, where you're inputting something into the machine, and it's doing something, and then your output is whatever it is that's being done by the machine. Usually it's some kind of a rule. The ones that I can remember in elementary school was when we were learning how to skip count, and it might be like a +3 or a -5 or something like that when we were learning how to do our basic operations. Now our rules or our calculations that are going to be done in our machines are going to be a little bit more complex than they were when we were in elementary school, but it's the same basic idea. So with the example we've been talking about with the rock dropping, the input would be the time interval, and it's being shown here as a t. I really like keeping my input as x's, but I guess Eureka doesn't agree with me on that one. But t can represent the time, that's fine, or it's x if you're thinking about the linear equations. The output would be the distance traveled in the given time period, or your y. When we input 3 into our machine, what is our output? So if we look back at the table, when we input 3 into our machine, our output is 144. So what's happening in the machine that makes the output come out at 144? This is kind of figuring out the rule in reverse, kind of backing ourselves into the calculation. So if we look at our outputs and look at our inputs, we think what's happening to our inputs to produce that output that will help us to find the rule. So let's talk a little bit about our inputs. The input is limited by the length of time it took the stone to drop and hit the ground. So when the person was standing on the top of the building or whatever it was, they dropped the stone. Your input is limited by the amount of time that it takes to start and stop whatever the experiment is that we're doing. We call that the range. It wouldn't make sense for us to continue timing after the stone hit the ground, because what we were trying to determine was how fast the stone was traveling at specific intervals between when it started and when it stopped. So the start and stop time would be the range. The output or domain, as it can be described as the function rule or the equation that defines the function. Okay. We learned in the last module that linear relationships can be shown in different numbers of forms, like tables, equations, graphs, and words. Functions are going to be the same. They can also come in those different forms. So we've already seen a table. We're going to see graphs. We're going to see equations. In fact, that's what's coming next. So right now, what we can do, we haven't defined the equation yet, but we're going to in a minute. Y is the distance traveled in the amount of time t, or x. Use the equation function y equals 16t to the second power to calculate the distance the stone dropped over in a given time. Remember your order of operations here. If you're using your calculator, where you're going to want to input it is 16 parenthesis t 0.5 raised to the second power close parenthesis to make your calculator do it in the right order of operations. The way I tend to input things is I automatically think about order of operations when I'm inputting things into a calculator, so I might put it in as 0.5 raised to the second power times 16. That would just keep those parentheses not having to be used. Regardless, what we want to do right now is put this into our calculator, and whatever number is up here is the number that's being raised to the second power, and then it's being multiplied by 16. So the first one I'll do for you, 0.5 raised to the second power times 16 is 4. Okay. 1 raised to the second power is 1 times 16 and 16. So continue doing those, use your calculator, and figure out the numbers going all the way up to 4. Go ahead and pause the video. Okay, so at 0.5 seconds, we're talking about 4 feet. At 1 second, we're talking about 16 feet. At 1.5, we're talking about 36. At 2, we're talking 64, 2.5, 100, and so on. Are the distance that we calculated equal to the table from lesson 1, or the table that's actually presented on page 9, which is the same table from lesson 1? So let's flip back over and just make sure that our equation actually worked here. 0.5 is 4, 1 is 16, 1.5, 36. Looks like we got it. It looks like that equation defines the function. Sometimes equations are going to define the function. Sometimes they're not. What do you notice about this equation, first of all? Is this a linear equation? Meaning if we graph this data, is it going to be a straight line? How do we know? Can we just look at the equation and determine whether or not it's linear? Who remembers what we need in order for it to be linear? And what does it mean to be linear? Lots of questions. If I'm looking at the equation, y equals 16t to the second power, I know it is not linear because it's to the second power. For the equation to be linear, meaning if the graph is going to be a straight line, it has to have either no exponent or the exponent has to be equal to 0 or 1. So, does the function y equals 16t to the second power accurately represent the distance the stone fell over a given time t? In other words, does the function assign t for the correct distance? Explain. I will say The function accurately represents the distance the stone fell over the given time interval. Each computation using a function rule or equation resulted in the correct distance. And the correct distance was gathered while watching a stone falling and probably like doing a slow capture and actually calculating the time that it took that stone to fall. And this is physics, guys. This is real world. People do things like this to figure out the physics behind things. So we're going to do a couple more things together, and then the rest we will finish in class tomorrow. Let's just flip the page one more time. Re-examine our definition on page 9 of a function. Can you think of why the phrase exactly one input, or excuse me, exactly one output must be in the definition? Think about it for a second. And then what I would like you to do before class tomorrow is come up with your own definition of function. Okay? So think about why the phrase exactly one output must be in the definition of a function, and come up with your own definition in your own words for functions. The other thing that I'd like you to do is examine a couple of tables here, 2, 3, and 4. I want you to look at these input-output tables and check to see if they represent a function. So are all of the, first of all, what I would suggest that you do when you're doing this is check the inputs. Are all of your x values unique? Meaning, are they all different numbers? If there are two inputs that are the same number, are they the same assigned to the same output or different outputs? So let's do the first one together. Looking at our inputs, we've got 1, 3, 5, 5. We've got 2 5s. So we already have a situation where not all of our inputs are unique. Now we have to check the output. See, 5 is assigned to 19 and 5 is assigned to 20. Again, I don't know accurately what prediction I can make with that. I've got two different outputs for the same input, so this is not a function. Again, it's not wrong, but it's not a function. So check table 2 and table 3 and table 11, and that is the conclusion of this lesson. At this time, we're going to finish pages 12 and 13 in class tomorrow, and then do the independent work. So just wrapping up real quick, and you could use some of this information for your summary, because yes, I will be assigning summaries as well. So the purpose of a function is to be predictive. A function is a rule or a formula that assigns each input exactly one output. Not every function is going to be expressed by a mathematical rule or formula. The rule or formula can be a description of the assignments, or it can be a way of figuring out the output for specific inputs. Functions have limitations with respect to the situation that they describe. So functions are sometimes described as input-output machines. Again, that example is on page 10. So that concludes this lesson. I'm under 20 minutes. Yay! See you in class tomorrow. Bye-bye.